Okay, so let us begin. Ouch. So yeah, you're right, and you're not the first one to ask me this. What is that notation? Alors, where did I define that? Yeah, over there. Ow. So you see, yeah, what you find in the literature was this exclamation mark. It was this exclamation mark. So if you start from an algebra, this is the Koszul dual algebra. But what I wanted to say this morning is that there is a more natural guy appearing, which is the Koszul dual co-algebra. So you see, how do you relate these two? They are exchanged by the linear duality. Okay, this is the Koszul dual algebra. This is the Koszul dual co-algebra, both of an algebra. See, and bon, so one way we found to describe them is the exclamation mark and upside down exclamation mark. Algebra, coalgebra. I think you used a perpendicular in your paper. We found that might be people might confuse it with that. So that's why we chose that notation. No offense. You can disagree. There's no problem. Okay. Does it answer your question? Okay. Okay. So this afternoon, what I have to do is I have to explain you how one can extend. So you see, the first talk was about operads.
Before you erase, can you just recall why it was clever to try that thing, or it was cheating? At some point you said it was cheating to try that, or clever.
What was clever? To do that? How do you compute A anti-truth?
Normally we should have done something else, but you said, okay.
I say that if you give me a quadratic data, and you ask me, Bruno, compute the quadratic coalgebra out of that, I cannot. Because it's very hard. These are linear, these are vector spaces. So how do you compute the intersection of these guys? So, okay, let me say it in that way. I'm too stupid to do that. But I can use this. So that's why I think it's a good trick. Take linear dual over quadratic coalgebra. It's a quadratic algebra. Oh, and then it has a nice presentation. You can compute it, and you go back by taking the linear dual.
So that trick is a proposition, it's just a fact.
Okay, mathematically speaking, it's a proposition. Okay, and then trust me, when you want to compute something, that might save you a lot of time.
It's because of what you learn in school.
Yeah.
You learn algebra. You don't learn co-algebra.
That's what. Yeah.
That's why it's easy.
Yeah. So now we have to begin. In France, we have a new law for will change the schools and blah blah blah. But they didn't think. I mean, they should include in the new law learn co-algebras in kindergarten. Just stupid. But okay. So. So you see, first lecture was operads, second was Koszul duality for associative algebras. Now it's Koszul duality for operads. So you see, I might not write everything, so I hope you have all your notes with you. But I will definitely try to follow exactly the same pattern. First thing is what? So you exactly have this diagram, and the ultimate goal first will be to extend that diagram from algebras and coalgebras to operads and co-operads. Okay, so that's the goal. Okay, so the first thing is that we need is to define a bar and a cobar construction. Bar and cobar, well, constructions for operads. Let me put maybe an operatic. Bar and cobar constructions. Okay, so last week we began with, we said, well, let A be an algebra. So here I take P to be an operad. Okay, so what is an operad? Let me remind you that it is a map from, it's a monoid in the category of S modules with the circle product. Okay. And this is associative, blah, blah, blah. Well, but what I need is the dual notion. So the dual notion is what? If I write it's co-operad, what does it mean? I mean, you take the definition of an operad and you reverse all the arrows. So you stupidly reverse all the arrows. So what is a co-operad? You take an S module. So in arity n, it's a formal space of operations of arity n. And you have a device, a way of decomposing these operations onto levels. That's all. Okay? So if I use the tree picture, if you take an element, say C in C5, curly C5, this gives you a way of decomposing this onto levels. For instance, something like that. I don't know. C prime, C second 1, C second 2. I hope that I don't want to record the circle product because it was complicated. So formally, this is the definition. And if you want to feel what it means, here you had two levels of operations that you were composing. Here you are going in the other way around.
Do you have a delta sub I? Like you had a circle sub I?
Exactly. This is a very good question. Sure. Here we have a co-unit. So we can look at the part where here I have only the identity except for one. Okay? And this will be a delta 1. So sure, among that, you could. What I would like to consider is actually delta 1 like this. I want to split 1 and do not specify where it lives. And I could then specify, say, oh, it lives at the highest place. But there is something I would need later, so I use the fact that you asked that question to introduce it. So there is one which is something like that. It's not real tensor. You see what I mean? Is that when I have a C here, I split only into two vertices. So it's not really a tensor. There is also the place where it lives. You see, here on that level I have just one vertex. And I have a total only of two vertices. This is the guy which is more or less the dual of the circuli, or the sum of the circuli. I will use it later. This is the infinitesimal coproduct. Okay.
I have a question.
Sure.
You said you reverse the arrows,
Yes.
but for a p-tensor P to P, there is an infinite sum.
Yeah.
Do you change it into an infinite product or not?
No, not here. So this is a sum, right? This is a sum over blah, blah, blah. This is not a product. So I just inverted the arrows. So I take exactly the same formula for this one. But you're right, if I want, the other thing I could do is I could take the linear dual. And if I take the linear dual, I should take invariance instead of coinvariance and products instead of sum. This is not what I'm doing here. To some extent, I will reduce myself to conilpotent cooperants. So only finite sums, blah, blah, blah. No.
Sorry, the thing in the bracket below the delta there is I or 1?
Sorry,
or
it's
what?
1. It's 1.
1.
1 because I have just one here on the second level.
Okay.
This one stands for this one is the same one than this one. These are the same ones.
Yes.
Yeah. This is the infinitesimal coproduct, infinitesimal part or linear part of the coproduct. Okay. So the first guy we considered. The first guy we considered is the convolution algebra. So what could be the convolution algebra here? And this is a key object. So this is a key object. So let me stupidly copy what we did last time. So definition, we were considering forms from C to P. Now what does it mean here? This is an S module and this is an S module. So this is the home space. I should take of S module. That is, you have maps from Cn to Pn for any n. Okay? Okay. But let me so far forget about the symmetry group action. Okay? So what is this? If you remember last time, this was a convolution algebra. So if I copy-paste the same pattern, that should be an operad. It is. This is an operad. So this has a structure of an operad. Okay? This has a structure of an operad. So for instance, you give me one operation f, which goes from C to P, and operation, so f, G1 to Gn, okay? And how do I compose them inside that operad? What can I do? So what is gamma of these guys? What can I do? Well, you start from C. You start from C. You apply delta. So you get trees with 2 levels. Okay? Now you live in C, circle C, right? You apply F here, J1, G2 to Gn. Well, maybe I should put a K here to be coherent with last time. So now we apply here F. So we get the same underlying shape for the tree. Okay? So we apply F, G1 to GK. Okay? Now we get something which lives in P, circle P, that we know how to compose in P. Well, it's the gamma. Okay? My claim is that this defines an operatic structure on this home space. Okay. But then, so that's what you actually saw in the very first talk by John. Each time we have an operad, there is a nice algebraic structure we can do out of that. So each time, so say lemma, if I take O and gamma O to be an operad, okay, I can consider the following the following guy. I can take, let's say, O. Here I want it to be the product over n of all O of n. This is my underlying space. So here I have a collection. Now I'm taking a space. Okay. And here, from this gamma, I will cook a new operation that I denote star. Okay. So what is star? What is star of 2 elements of my operad? Star. So what is P star Q? That is, I will take the sum over all i's equals 1 to k if P lives in O of k of P circle I with k. Okay, so do you see what I'm doing? I'm doing the following thing. What is P? What was that? That is the sum of all the possible ways of composing P with Q inside my operad. That's the sum of the circle I. Okay? Well, we can define that. That's a vector space. That's an operation. And what does this map satisfy? And I will do the computation because it's easy. No, I want to keep that. Okay. So what do these products maybe we can check whether it is associative. This is something we know. So let us try what if this guy is associative. So what is P star Q minus star R minus P star Q star R. If this is associative, it is 0. Okay. But anyway, let us look at what this guy looks like. So, what is B? P star Q star R. Well, So first you take, so you have a sum, okay, of. Alors, you first take P, okay, and you plug Q above that. That's my first bit here. And then I plug R above that. Oh, but there are two kind of terms. The two terms are either I put R above or I put R next to Q. Okay, so there is another kind of terms, which is something like that. Okay, so sequential composition or parallel composition. And if you remember the definition of the circle I, then I don't need to put the parentheses. This is the only kind of that I have. Okay. And what is this? Here, you first do all the possible ways of plugging R above Q, and then you plug this result on P. Okay? So, what you have here is these, you have these two times of terms minus this one. So then you see that these two, they cancel. Only remains this. Is it 0 in general? No. Well, it's not 0, but why should we look at 0? We look at the guy we have and see what he satisfies. And here, what you see, you have this. This is the associator, but it satisfies something quite nice. It is symmetric in terms of Q and R. Why did I put Q on the right-hand side and R on the left? I mean, I take the sum of all of them. So actually, this guy is equal to the same one, what I change the place of Q and R. Okay? Okay, this is, okay, so here, then we can give fancy names to that. But if you consider that star operation, it satisfies this. The associator is right symmetric. And there is a name for that. Such an algebraic structure is called a pre-Lie algebra. In English, pre-Lie algebra.
The identity is Windberg identity.
Yes. Yes. Okay? And why the name? I mean, there's Lie and pre-Lie. Because it comes before Lie. Why? Because then now what you can consider is you can consider the bracket PQ defined by anti-symmetrization of your star. So you do that, well, up to sign that I don't want to make explicit. You anti-symmetrize your guy. And then you check the Jacobi relation. The Jacobi relation will give you the sum of 12 terms. And 12...
You got an R, you make P.
R is P here, sorry, thank you. So, if you write down the Jacobi relation for that, it will give you 12 terms, and 12 is 3 times 4. And here we have 4, and trust me, the Jacobi relation splits into 3 times a relation of this shape. So yes, this is a Lie bracket. Okay, so in the end, where is it? In the end, the convolution operad is definitely a nice object, but what I am going to consider is actually the product of all these guys with this star product. So this induces also a pre-Lie algebra, and it induces a Lie algebra. Okay? By taking the product of all of that. So let me do it. Anyway, now, let me do it, and we don't want just maps from Cn to Pn. We want maps which are equivalent with respect to the action of the symmetry group. So actually we want this. But this breaks the operad structure. This breaks the operad structure, but still you have this survives. So on the space of these invariants with respect to the symmetry group, you still get that structure. So what I mean now is I will really take this notation will stand for that. Okay. Then with either the pre-Lie bracket or the Lie bracket. Okay. So we recover the same kind of ultimate algebraic structure. You remember last week we had that this guy, the analog, was an associative algebra, and inside that I was considering the Moore-Cartan equation. Okay, so here we can continue to consider the Moore-Cartan equation. In that context, it will be that, but which I am working over a field of characteristic 0. So with degree -1 elements, so this is equivalent to the classical Moore-Cartan equation in the Lie algebra. So we can continue, we can pursue the analogy with what we had last time. So this is the convolution Lie algebra. Lie or pre-Lie algebra, whatever you want. Okay. Then, if you remember last time, we added into the picture, the differential. So now, I should give you not only an S module, that is a collection of vector spaces, but I should give you a collection of chain complexes. So D means that for any n, P of n is a graded space with a differential. I will not make all the details here precise, and I will not cheat, but we saw that you can define the notion of an operad over any symmetric monoidal category. Well, the category of chain complexes admits a honest tensor product, with sign rules, blah, blah, blah. So you can do operads over that. So now it's an exercise, actually the first exercise of the sheet for today, is that take this underlying category and describe what it means. For instance, for D being a derivation with respect to that. It's very easy. I just want to continue and not giving these details which do not explain more. Okay.
When you say chain complex, the differential is always of degree +1.
For me, it's degree -1. For me, I'm working in homology here. I'm algebraic topologist. I'm working in homology here. No, yeah. For me, all the time here, D is equal to -1. All the time. All the time. So if you do that, and the Moore-Cartan elements, they have degree -1 too. Okay. So then inside this picture, now you add exactly the same differential, the same kind of differential we had last time. If you have a map from C to P, what is the differential of that map? You apply the differential at the source, then F, minus F, and then the differential at the target. So this is nothing new. So since it's not new, I'm not making the details explicit. So then we get DG pre-Lie algebras and DG Lie algebras. So differential graded.
So a map from C to P is a collection of maps from Cn to Pn.
Yes.
Cn and Pn are complexes.
Yes.
And that's complex.
Exactly. It's a home space, just yeah. There's nothing hard here. Oh. We have the first.
The map are not map of complexes, are they? Otherwise, what is their maps of complexes?
Hold on.
Yes.
No. Sorry, they are not map of chain complex, right? Because a map of chain complex is a degree 0 map which commutes with the differential. No, they are any map. No.
Now the differential on the moment
But the differential is this.
from one complex to another one.
Yes.
And then the H0 is what you
Yes. So you see, we have the first analog. We have it. Can we continue? Sure. So here, a twisting morphism is a collection of S equivalent maps of degree -1 from C to P. That's easy. Okay. Now I want to represent this bifunctor. So can we first try to represent this? Yes, exactly in the same way. I need to put my operad P here. I want to look at that in the category of operads. So what has to change here? Well, I should change the free algebra by the free operad. So you remember, T stands for trees. You have a realization of the free operad by trees. You desuspend, so for any n, you desuspend all the guys. You take your co-operad, and inside that, you kill the identity. So this is exactly the same. On the right-hand side, you have a co-operad. I take C. What do I have to replace here? I have to take the co-free co-operad. Alors, I propose that we don't do that right now. Just what is the co-free co-operad? It's again trees, and you cut the trees into two. So you degraft them, you cut them, you know, and this produces a co-free guy among co-nilpotent co-operad. I propose that we hide that under the carpet a bit. It works the same, but I don't want to give you all the details. But it's the same. It's trees. You just cut them along one level. Okay. Wow. So we have the first line. Okay. Now we have to extend the bar and the co-bar constructions. So how can we define a differential here and there such that we have this result? So let us now, I think this deserves more study. So now I want to represent that in the category of DG operads. So here the point is to define the co-bar construction, and this is in the category of co-operads, and the point is to define the bar construction. So let us spend time understanding this. Ouch. I wanted you. I need you. So. Okay, so let us begin with the co-bar construction. Okay. So, the co-bar construction should eat a co-augmented co-operad. You kill the unit inside that, you desuspend it, and you take the free operad on that. That's what is written on the top left corner over there. The only point now is how to define a nice differential on this guy such that the isomorphism on the second line hold. Okay. So, well, if you find this complicated, let us draw a picture. What's that? That's trees, vertices labeled by that. That's trees. And the vertices are all labeled, according to the arity, by element of this. So, for instance, here you have an element which comes from C2, and you shift its degree by -1. That's all. The element here is an element come S -1 of C3, and so on and so forth. Is that okay for everybody? I am taking the free operad on this collection, yes.
So a tree, and at each vertex you put something from the
I label each vertex of, yes. You know, and because the generators is shifted blah blah blah, this is if you want to take care of the homological degree. Otherwise, if you want just to have an idea of the underlying guy.
Maybe I missed something, but what's a twisting morphism?
Sorry, I didn't say it. Solutions to the Mohr-Cartan equation.
No, in the operatic setting.
It's a solution to the Mohr-Cartan equation. There's nothing new. You have a honest de Gilly algebra. You have the honest Mohr-Cartan equation, and you say that an operatic twisting morphism is a map of degree -1 from C to P, which satisfies that equation. There's nothing new. I mean, you're right. I didn't explicitly say it. Yes, exactly. Okay, so we have these guys. Well, now you remember that last time when I defined the co-bar construction, I defined a differential D1 and a differential D2, and I took the sum of them. So let us do this here. And I copy-paste, and then I will plug my brain and try to understand what it means. So what did we do last time? We chose D2. Yeah. So last time we said, well, we're working in a free algebra. So in a free algebra, derivations are completely characterized by the image of their generators. This property is, of course, again, true for operads. So here I have a free operad. I want to define D1 and D2, two derivations. So what I will do is I will define them on the generators, extend them, and finally I will try to think a little bit and make them explicit. So D2 is the unique derivation which extends what did we do last time? We took S minus 1 of C, it's a straight C. We applied delta, okay? And this was arriving is in S minus 1 of C times C, okay? No. So now let us put some curly letters. I have to split C into 2. So here I split into 2, so I use my infinitesimal decomposition. Infinitesimal decomposition now. Okay. So now this guy lives again in C times C. Okay. So let me draw a picture. You have a corolla, okay, labeled by S minus 1 of C. Then what do? You split that corolla according to the co-operad rule. And there is an S minus 1 in front of it. That's exactly this. Okay? So this is actually not tensor. So I should remove that tensor and say these are trees with labeled by C. Actually they are labeled by C bar. Anyway. And 2, this stands on the number of vertices. Do you follow? I start from an element in my co-operad. I use not my full delta, but the infinitesimal part. I just split into 2. Keep in mind that ultimately, I want this map to live there. Let me just forget about the unit. So how can I go from here to there? Well, so far I do not have a tree which is labeled by S minus 1 of C, S minus 1 of C. So I have to add one S minus 1 and label it here. So I just desuspend this guy. Okay, so I'm adding one S minus 1. And then I put one S minus 1 here, and I put the other one there. This lives where? This lives in the space of trees, labeled by S minus 1 of C, with 2 vertices. And this lives inside the space of all the trees. Is that okay? Last time I was splitting guys into 2, properly desuspending, and embed that in the free algebra on S of C. Here there's just a tree shape something. I split guys into 2. Okay. Okay, this is D2. Okay? Now, it is well defined. It's a derivation. And you might say, well, it's defined by a universal property, but what is this guy? Okay, let's try. So what is D2 on a tree? Okay. You will apply, last time we said, oh, the extension is you apply D2 everywhere you can. So let us apply D2 everywhere we can. So D2 of such a tree is given by the sum of you apply D2 here, or you apply D2 there, or you apply D2 here, or you apply D2 there. So you take the sum of all the possible ways. It's a proposition, I mean, not so deep proposition, but I mean, it's a result. This is the definition, this is the form of it. Sum over the vertices of, and then you have another sum which is given by this delta. So which one should I do? For instance, this one. See. Okay? And this is s minus 1 of c to second, s minus 1 of c primes 2. So you see, for instance, I can apply my delta here and I explode this vertex into 2. That is vertex expansion boundary map. And it definitely comes from Koszul paper in 93. So this is...
Are there signs?
Hmm?
Are there signs for this?
Yeah, of course. Yes, of course. There are many signs, and wow, and here. Okay, you see the s minus 1 is coming here, and I'm coming with another one. And then I have to shuffle them, permute them a bit to put it here, first sign. And then when I apply D2, I should put a global sign on my global order on my vertices, say above which D2 jumps, and then apply. So please, I don't.
There's no magic wand.
But okay, plus minus. Okay, so what we did, for all the vertices, we exploded them into 2. So this is the vertex expansion à la Koszul.
Anyway, the tree should be planar, right?
No. No. This is a blackboard, so I'm writing planar trees, but the trees are in space. This is operads, not non-symmetric operads.
No, but if you change the tree by
Yeah.
an isomorphic copy, you have to change the labels accordingly.
For me, they are in space. So if I have labels, but you know, delta is a splitting in space. You have a corolla, and you split it into trees in space with 2 vertices.
Yeah, but the way you say you compute the sign seems to depend on the embedding.
No.
What is the
oui.
The free operad on a symmetric collection?
Yes.
You have to take planar tree, isomorphism plus. Well, let's not discuss.
Yeah.
But it's not going to work, and therefore you can put the right signs.
Alors, actually no.
I
Okay, let me say. Okay, here is one way of describing the free operad. It's given by a certain colimit of iteration of the circle product. Then I can pick representatives. And if I pick representatives, the signs I had in that colimit then gives you signs. But on the representatives, which are planar trees, but vertex expansion. Okay. But just it's a remark because the Koszul duality theory was known in the 1970s by Pridi. I imagine people wanted to do that for operads. And I read in Ginsburg-Kapranov, they said, well, we didn't know how to define the bar and cobara construction because these are the first constructions we need for Koszul duality theory. And they said, wow, it is thanks to Koncevich paper in 93, the paper about graph homology, that yes, we saw how to define a bar and a cobara construction for operads and cooperads. Therefore, we were able to continue and define. So this is not a free remark. It's more deep than it appears. It's not that deep, but okay. Okay. Then, okay, you have understood the hardest part of the construction. So let me just say what you do. You define D1 to be the unique derivation which extends. Let me erase it. Then we do exactly the same thing as, let me do that. Oh, I should just erase that.
Why do you say D2? That's my question.
Why is it D2?
Yes.
Why 2? Because you split into 2. It's a co-algebra something.
Oh, and D1 will not.
D1 will be an internal one.
Okay.
Will not change the number of vertices. Yeah. So D1 is really, okay. Again, you have D1 of C. So what do? You apply D of C. So D of C will produce an element in S1 of C. And this is a tree with one vertex that we embed here. Okay? This is a degree minus 1 map. So it will produce a degree minus 1 derivation. Great. So you just apply. And then proposition, which is D1 of a tree. Well, you just apply DC here, DC here, DC here, and DC here. It does not change the shape of the tree. Okay, so here it's easy. This is the sum over all the vertices of what? Okay, blah blah blah. No, I should write them.
Like in the bar construction, standard bar construction, you have to count.
Exactly, it's a tree-wise bar construction. the bar construction, you put guys one next to each other. Here, they follow a tree shape. It's nothing new. It's just
No, but I mean in the ordinary bar, the differential is sum of two.
exactly. And now, what you define to be the co-bar.
The inner one and the outer.
Exactly. Now, the differential is the sum of the two. It was a derivation. Both were derivations. So this guy is a derivation. Okay. And so this is a differential graded operad. Okay. And that's the co-bar construction. And the notation is the same. Omega of curly C. See, so the only thing which was new is, say, a bit this differential. So please, and I don't want to do this proof because it's exactly the same proof as last time. The commutation with this kind of differential amounts exactly to the Moore-Cartan equation. Commuting with D1 will give you the curly D part, and the commutation with D2 will play with the coproduct and the product, so that will give you the star part of the Moore-Cartan equation.
In the ordinary bar construction, you often have modules on either side, and there's a differential. So
Yeah, this is
there
really,
an
yeah.
analog to this?
That's what you call the bar construction. I would call that bar construction two-sided or with coefficients. So yes, you can start from this guy and add modules on the left and on the right, but with the proper tensor product, which is the circle product here. So yes, we can definitely do that. That's not the one I'm considering here, but one can do that for sure. Yes. Okay. So, but now the bar construction. So what is the bar construction? You dualize all the arguments. Let me try maybe to sketch quickly what it looks like. But if you need more details, you tell me. You take the co-free co-operad on. You take your operad, you kill the unit, and you suspend. And then you take trees on that. So it's the same kind of, guys. Okay, so except that here I have suspension of P3, suspension of P2, etc. Okay. Okay, that will produce a DG co-operad. Okay, let me just do D2. D1 will be of the same shape. So you define D2 to be the unique co-derivation. So now I should put T of C. So a co-derivation is completely characterized by the projection onto the cogenerators. Okay? So what can we do? We do exactly the dual thing. We have trees labeled by P. We kill everybody except trees with two vertices. Okay. Then when we have that, we desuspend and remove the S with proper signs. I am, of course, cheating here. So this is S of trees labeled by P bar with two vertices. And now I have a tree with two vertices that I can compose with the composition map of P. Okay? And now there is a unique co-derivation which extends this. What does it look like? Well, you apply it everywhere you can. So this amounts to what? This amounts to contracting every internal edge and multiplying all the vertices, the associated vertices. So D2 is, let me forget the labels. And then this is the sum over, internal edges. Okay. And then you contract. So for instance, delta 5. Okay, so you see, for instance, I chose to contract that edge. I chose to contract that edge, and it gives me this tree with proper labelings of element of P. That you want me to draw the labelings? No, that's okay. So this is edge contraction. Again, according to Koszul. And this defines a proper chain complex. Okay. And the bar construction, well, you add the internal differential of P, and you get that bar construction. C'est quoi la question?
No.
Si, si.
No.
Feel free to ask your questions. Okay, so we have now, on the left and on the right, the operatic bar and cobar construction. And by the same proof as last time, these two bar and cobar construction, they represent the twisting, the operatic twisting bifunctor. Okay? Since the bar and the cobar constructions, they represent this functor on the left and on the right, they form a pair of adjoint functors. So we have exactly all the result. Now we are back to what we did this morning. So the bar and the cobar construction forms a pair of adjoint functors. They admit universal twisting morphisms. Let me maybe write a bit. If I go too fast, you'll be lost, I fear. Okay. So what did we say this morning? Okay, it forms a pair of adjoint functors. So you start from augmented DG operads. You go inside co-augmented and actually co-nilpotent, whatever that means, DG co-operad. Okay. And omega is the left adjoint. Okay. Any twisting morphism from C to P factors uniquely through universal twisting morphisms. Okay. Exactly the same. In the arguments I gave this morning, there are general arguments for a pair of adjoint functors. So there's nothing new at all. Okay. Wow. Good. Now, I forgot the motivation. I plan to motivate all of that, and I skipped.
So could I,
Shall I?
could I ask a question? You have this
Sure.
diagram on the right that's
Yes.
you're in the process of changing. What are these isomorphisms of?
DG.
In a symmetric case, okay, just
Okay. The only difference between this and that is the differential. You ask that your maps, they commute with the differential. So this is an equation which amounts to the Mohr-Cartan equation. So that's the only new part from here to there. You add the differential. You take the differential into account. Okay. The motivation comes from we want to be able to check whether or not we have quasi-isomorphisms. Alors, give me a second. What should I do? Let me finish with this, and then I will make a break and give you a concrete example exactly in the same way as I gave this morning with the algebra of neural numbers. Why we are doing that? If it's okay. Okay. There is a very natural question here. We have maps of differential graded operads. Are they quasi-isomorphisms? So now what I really want to have is a simple criterion to say when they are quasi-isomorphisms. So here I can state that, no problem. Here I can state that, no problem.
Also in the middle.
But here I have to work. This was easy, I mean. I have map of chain complexes as they are quasi-iso. This I know the definition. But how to define the notion of Koszul morphism now in the operatic context? Here we have to work a bit. Not that much, but a bit. Oh, Alors. So, what are operatic causal morphisms? Okay, so you remember that this morning we considered C times A. So what, and we twisted this classical tensor product. What takes the place of the tensor product for operad is the circle product. Yes, because an operad is a monoid there, and a co-operad is a comonoid. So now let us look at the following construction. I take C, circle P. Okay? I claim that this guy does not have exactly the same shape as this morning. That's nice to just write circle there. But you know, this, the tensor product, was symmetric, linear on the left, linear on the right. This guy is not symmetric because, for instance, it's linear on the left and not on the right. So I need to work a bit more to twist this circle product. This guy looks like what? You have C like this, and you have several elements from D on another line here. This is C circle P, okay? So this morning, what we considered is, of course, the differential on C, the differential on P. Well, already here there is a difference, but so we can take the differential on C, circle the identity on P. What is the effect of that map? You take such an element, and you apply the differential of C to that element. That is okay. If I write this, I'm wrong. And unfortunately, you see it in many papers. What's the meaning of that? The meaning of that is that you apply the identity on that level, and you apply the differential everywhere. This has very few chance to be a degree minus 1 map. Okay? The way to fix it is, let me write maybe a circle 1, or I think it's prime in the book. So you take a linear version of that map. That is, you leave C, and you apply D here, plus you apply it here, plus you apply it here. Then this becomes a degree 1 map. So you see the first... and then how do we twist? So you remember, this morning I added a twisting term. And the way we defined it is we were splitting C into 2, applying alpha in the middle, and then multiplying it. Here we have to be careful, because if we apply delta, if we stupidly copy-paste what we did this morning, we will apply delta, and we will create maybe 2 or 3 C above, and we will apply alpha to these 3 guys. Again, this will not produce a minus 1 map. So a good definition is the following one. So what is D bar of C? You take C here, and you apply again the infinitesimal decomposition. So you split that guy into 2.
Sum of.
Yes, because delta produces a sum, as usual for coalgebras. I can use some kind of Swidler notation if you want to remove them. Okay. So you see, I really want to split into 2 guys, not 2 levels. And then I can do exactly the same. That is, now on this element here, I apply the map alpha. And that map alpha has degree minus 1. And now I have here an element and several elements in P that I compose inside the operad. Okay, this is the D bar. Okay, Just you need to properly linearize at some places and not stupidly applying exactly the same formula. So you see, degree 0 map, degree -1 map, degree 0 map. So it's a degree -1 map, okay? And exactly in the same way as I proved this morning, so that you have exactly the same lemma, that is, alors let me define this full guy to be the twisted differential, okay? Lemma, again, I won't prove it, but no, hold on. If you square d alpha, this is d bar, or curly d alpha plus that. And so you get exactly the same thing as this morning. That is, when alpha is a twisting morphism, you get a chain complex. Okay? And so in this case, okay, so definition, we call that the twisted composite product. Okay, and notation for that is the same as this morning. Like that. Okay, so we have the analog of the twisted tensor product in that context. Okay, good. Do you have any questions?
This morning you made a difference between C tensor A and A tensor C.
That's a very good question. That's a very good question. So this morning, when we were twisting the tensor product,
It's all staged.
the underlying module was the same, but here it's not. So you're right, it's a good remark, be careful. The underlying space is the same. Okay? Therefore, the definition of d alpha is similar. We take the mirror dual in the simple meaning mirror dual.
So
But
if you make this identification, it's the same.
It's this morning it is the same.
If you just exchange.
Yes. The definition is similar. I do not claim that this isomorphism of vector spaces give an isomorphism of chain complexes. It's similar. But here, no way.
Okay.
So if I had 5 more minutes, I would draw this as trees with 2 levels, and I would define how you twist this one. This is not the same similar formula. So no, but okay. Tell me if you need it. I don't think so. Let me propose this. Try to do this tonight.
In your statement, there were 2 equivalents.
Exactly. I will write them. But already here, it's less trivial than this morning. Already this morning, it was not that completely trivial, and it's even less trivial here because of that. So you see, already on the level of the underlying space, they're not the same, and therefore the differential is not the same. So sure, yes. But this is a good question because now I'm going to give a definition. You will tell me that's a bad definition, but then with the theorem, it's a good definition. Okay, we say that alpha is a Koszul morphism, or operatic Koszul morphism. Koszul morphism when the twisted tensor product is acyclic. Okay? So now there might be an ambiguity. You see, we could have this guy, we could have this one being acyclic and not this one. Actually, no. Okay, and then, so the notation for that. Now we have we have all the ingredients now. Okay, we have all the ingredients. Okay, and you're right, now you need a theorem, this isomorphism. So the theorem is the same. Under weight grading assumption. The following assertions are equivalent. 1. The twisted tensor product, composite product is acyclic. Second, the other one is also. And this is here a highly non-trivial result. Well, non-trivial result. More or less, yeah. It's not Riemann hypothesis. And then in this case, if you look at the Kobar construction and the map F alpha, this is a quasi-isomorphism. And all these are equivalent to C being quasi-isomorphic to the bar construction, which can be summed up here by saying that. Okay, so we have exactly the same theory.
You say a very brief word about your assumptions on weight grading? Just orally, just say what.
No, you're right. Let me. So yeah, we want to have some kind of spiritual sequence argument. And so here what we are going to ask is that these two guys, they come equipped with a weight grading, and that the twisting morphism preserves this weight grading, so that we keep track of everything. Let's say we have no extra degeneracies, so we can control them. I can be more precise later if you want. It's for the technical arguments. I think to understand the theory. Let me not do what I did this morning, because the proof follows the same pattern. We prove the same kind of comparison lemma. You see, so this morning we said, well, if we want to compare two twisted tensor products, if two of the three maps are quasi-iso, then so is the third one. It's a 2 out of 3. Exactly the same thing here, and blah blah blah. So, but with the same remark, I mean, example, I have first to prove that the universal twisting morphism, so iota and I, this is curly C. So we have to prove exactly the same thing this morning. That is, for instance, the augmented bar construction for an opera. This is always acyclic. Okay, so John did that for us in his paper with Ezra, so that's okay, it works. So these guys are Koszul morphisms. Thank you. Okay. Yes.
So I'm coming back to the question Francis asked earlier. C circle alpha P, is that a CP bimodule?
Yes. Yes. Well, whatever that means, CP bimodule. This is a co-module here, and this is a module there. Yes.
Right. That's what I meant.
Yeah.
And so all these things are isomorphisms of bimodules in this sense too.
No. This is an iso of sets. This is the set of quasi-iso. This is the set of Koszul morphisms. These are quasi-iso of DG operads.
I'm sorry.
Okay. No. I did not extend. No. Okay. What do we need to do? Motivation and examples. But
So you're saying all these objects will be filtered somehow.
more than that, graded.
Yeah. So very roughly, orally, what's the
Oh,
the part which is the filtration, which is smaller than A? I mean, very roughly.
For a very good reason. For what I'm going to say after, the kind of operads I will consider, they will be quadratic operads. That is, with generators and the relations will be homogeneous.
Mhm.
So we get a natural weight grading. Think at the free. I mean, the point is here. It's here. You see, this guy is naturally weight graded by the number of vertices, the number of generators you dot. Everything
all.
comes here.
Yeah.
That's all.
Basically,
that's all.
the number of vertices.
The number of vertices.
Okay.
Dot. Yeah. Okay. Have we finished? With part 2. So I think you have the theory, except it's hard to digest. New letters. It works well. Blah blah blah. So let's try to unveil this a little bit. I propose to give you a motivation, then go to Koszul and explain you more. Try to explain you more. And I think I won't have much time today for the method. Let me try to give you the motivation why we do. Oh, no. There is a nice corollary, and then we have the motivation. You remember this morning we said corollary of that. Okay? Because these guys are Koszul morphisms, we have that the co-unit of adjunction is a quasi-iso. So, corollary, if we take the bar-cobar construction of an operad, that's always a resolution. So this is the bar-cobar resolution. And let me copy-paste the comments I made this morning. It is a functorial resolution. Wow! So it works for every operad. Wow! But what is the size of that guy? Let me forget. Yeah, again, this morning it was twice tensor modules. These are twice trees. So these are trees of trees. Oh, trees with some length on the... So this is what? You take trees off, let me forget the suspension, blah, blah, of T. Okay, so these are trees of trees. Okay, and you label. So this is exactly what Ike explained during his talk 2 weeks ago. That's the Bormann-Vogt construction, but in the context of chain complexes. So how do you pass from topological ones to chain complex? Well, in the one he had some length on the internal edges. Okay, so when I pass here from topological spaces to chain complex, let's say I have nothing between 0 and 1, so I just have 0 and 1. So let's say this length is 0, this length is 1, this is 0. And now if you look at the trees which are separated by 1s, they are then labeled by 0, so this is subtree, this is subtree. So this is exactly the Bormann-Vogt, resolution.
All the vertices have to be labeled by 0 and 1.
Exactly.
2 colors.
Yeah, exactly.
But strictly speaking, if you want to repeat what I said, so length 0 disappears because they're being contracted, right? So the zeros are really the generic length of delta 1.
So
You have 0 and 1/2 and 1. So to speak.
okay. Yeah.
Because 0 disappears.
Yeah. So maybe I should put 1/2 for the 0, 1. We only have interval and 1. You're right.
Exactly.
Sure. This analogy is better. Sorry. Yeah. And then you see what is the differential here. We can either split this into 2 or contract that. Oh, that's exactly the
1/2 can go either way.
Exactly. Has to choose. Yeah, to left and right. Okay. And then this allows you to, so this morning we used this resolution to compute some homology. So why now? Let me go back to what I should have done, motivation. So now it's very basic. So I hope I will have time to do both. Let's see. So what is the motivation? Exactly following the same example as this morning. So sorry, prequel motivation. So why are we looking for 3 resolutions of operads? So let me say exactly the same as this morning.
That circle at the left is 0?
Sorry? The third is 0. I forgot it.
Okay.
Yeah, I forgot the motivation.
Yeah,
It's very bad.
no,
Yeah. So exactly in the same way this morning, this is, you take an operad, differential graded or not, anyway, an operad. I am looking for, good reasons, a quasi-free operad, which is a resolution of that operad. It's exactly the same thing, you see? So this is a quasi-free resolution of P. So quasi-free means, again, if I forget the differential, the underlying guy is a free operad. It's just trees labeled by a labeling set X. So that's just trees. Okay. So this is the free operad, and these are trees. Okay. So I will give you one example, but here I will not derive a functor. I will give you another motivation for that. So let me call that P infinity. And again, so if you read Ike's paper, for instance, there is a nice model. There's a nice model category structure on operads, and these guys are cofibrant. For the experts, this is wrong. I need an extra filtration on the generators. Okay, for those of you who don't know, let's say these are good guys. Why do we want this? Look, P is definitely modeling the category of P algebras. Okay? But P algebras, they do not always have the nice homotopy properties we want. And I gave you an example 2 weeks ago, and I will fully develop it next week, is as follows. If you take two homotopy equivalent chain complexes, okay? Take, for instance, a deformation retract. I don't need this full structure. So def retract means that the composite of I with P is the identity, there's no problem. But in the other way around, it is not the identity. It's homotopic to the identity. So what does it mean? I do P and I. This is not the identity of A, but it's homotopic with the homotopy H. Okay? So that. You know, if these two guys...
Plus one. You say, oh no, P minus. P minus.
So, if I have a certain algebraic structure here, let me give you two examples. Let's say that here I have an operator delta which squares to 0. Example 1. Or, these are the two examples I say sketched, if you remember 2 weeks ago. And example 2, I have a binary product. So A is an associative algebra. Okay? If I have two spaces which are isomorphic, I can transport the structure. I can transport these guys from the left-hand side to the right-hand side, and since I have isomorphisms, they strictly satisfy the same kind of relations. But here, no, we've deformed the notion of isomorphism. So now, this squares to 0. What is going on with the transported guy? And in general, it does not square to 0. So for instance, this one. So what is the analog here? Let me denote it by delta, the transported D. What do? You do I, then you do delta, and then you do P. Okay? So you transport your delta. Does delta squares to 0? No. And this is why spectral sequences exist. You do the same with mu. So you transport your mu, let me call it mu. And this is what? You have elements in H, you make them live in A, you do the product in A, and you come back. Is this guy associative? No. And this gives rise to the Massey product. Okay, so I will explain this next week, but the motivation is the notion P algebras are not stable under homotopy equivalency. So we need to find a bigger category in which P algebras sit, which have nice homotopy properties. And this is exactly what conceptually we have with model categories. That is, since this guy is cofibrant, and here we have a quasi-isomorphism, so here we have the category of P infinity algebras. Okay? By pulling back along this map, okay, this is the frontal. So this category sits inside that one, and because it is a resolution, the homotopy properties you want here, you can read them there. So that's what I'm going to explain you next week. But I hope it's a good enough motivation to say I would like to understand the homotopy properties of P algebras. For instance, you come with a certain algebraic structure, and you would like to know what is the algebraic structure on the homotopy equivalent guy. What is this structure? I tell you, it's easy. You resolve your operad, and here is the new algebraic structure. So this is a P infinity algebra. So this will give you a spectral sequence, and this will give you an A infinity algebra. So this is what I'm going to explain next week. Okay? So that's why I want to have quasi-free resolution of operads. Okay? So we have a first resolution here, but it's huge, right? You see, for instance, what is an algebra over the bar-co-bar resolution? The number of operations. So what is an algebra over that? The generators, they will be labeled by this set, so this vector space. So I will have operations and one for each tree with vertices labeled by P. I leave you to imagine how big this algebraic structure here. So that is, so what I want is take something smaller here. Okay. Let me now give you one example, and then I will sketch the Koszul duality theory for operads. Let me do the same kind of example as the one for the algebra of dual numbers. So now we are really killing homotopy groups step by step. So let me start. So example. Let us do example 2, because we did example 1 this morning. So this morning we saw that what we should have here is infinitely many higher deltas which satisfy something. You remember? Delta 1, delta 2, delta 3, and so on and so forth. Okay. I will do this one now, naively, by hand. So I take as the non-symmetric operad of associative algebras. So you remember, last week we saw that this operad had a presentation, which is this one, okay? So what does it mean? Pierre is not here anymore. But let me explain you.
Okay.
This guy is weight graded by the number of generating operations. So what's the weight? What do we have in weight 0? Weight 0, we have the identity map. Well, that's okay. What do we have in weight 1? Well, we have the generator. What do we have in weight 2? Well, in weight 2, we could have two guys here. Okay, so this is degree 0 element. This is degree 0 element. So let me depict them by points. Okay? But they are equal, because we mode out by the associativity relation. Okay? And let me write what's going on in weight 3, so RET4. Well, you have 5 guys that you can a priori cook with the binary product. Here are the 5 possible composites. But inside that operad, all these guys are equal. Okay? So we get 1 point per RT, 1 point per weight. Topologically speaking, these are 1 point, 1 point, 1 point, 1 point. All these guys are in degree 0. Let me try to resolve that. Okay. We are going to take the free non-symmetric, so these are planar trees. Free non-symmetric operad on something. Okay. This comes always equipped with an identity, so there is no problem here. Okay, I have a generator. I have to put a generator here. Let me represent it like this, and it has degree 0. So this is a degree 0 element. Okay, so now I take the free non-symmetric operad on this generator. So in weight 1, I have just 1. In weight 2, I have 2. In weight 3, I have 5.
Same 5, no?
Wait, 5?
The same 5.
Exactly the same.
Yeah, exactly, sure. Yeah. But something will change inside. That's why I spend time writing. You see, so far this is what I have. On the right hand side, it generates all these guys. And 1 is degree 0, so when I plug 2, it's again a degree 0 element. So that's why I represent them with a point. Okay. So now, are these topological spaces homotopy equivalent? Sure. Well, these guys, they are the same. But here, no. We have 1 point, 1 point. So here we have 2 points, and here we have 1 point. So they are not homotopy equivalent. So here these guys were equal, so now I will relate them by introducing a degree 1 element. So I'm adding one new generator to kill this thing, is degree 1. And if I want this to be related to that and to that, algebraically speaking, I define d of that to be equal to this. Oh, I said nothing about the orientation, let me take this. Okay, so this means that you plug these two guys there. So then, no problem. These two are homotopy equivalent. Let's continue, but now I added one generator. Okay, so this generator will generate 5 trees with arity 4, namely these 5 trees. So here, what could I do? I can take this tree, okay? It's a degree 1 tree because this has degree 1, this is degree 0. And what is the boundary of this tree? I split on the left or on the right. On the left it is here, on the right it is there. So it relates these two guys. Okay? Well, let me write all of them. Let me do this one. So I can consider this tree inside my free operand. This guy has degree 1 because it's degree 0 and degree 1. But what is the boundary of this? I can split on the left and I get that guy, or I can split on the right and I get this guy. So, and so on and so forth. Okay? So, well, anyway, should I write all of them? Yes, let's do it. Okay. Now, is this space homotopy equivalent to that space? Not yet. Not yet. This is a point and I have a loop. So I need to introduce a 2 cell to kill it. That I'm going to glue along this boundary. Okay, so algebraically speaking, it means that if I pass through the chains, it means that I introduce a new cell of dimension 2. Those boundary is let me choose that orientation maybe. Okay, so this is okay. Exercise, I mean, we are out of time. So what is going on in arity 5? So here you will get 1 point, but here you will have 0 cells, 1 cell, 2 cells. Oh, this is going to form a nice polytope that you have to fill to kill that homotopy group. Oh, you will introduce a 3 cell, and so on and so forth. Okay, so you see, it is exactly the same kind of story that we had this morning. We wanted to resolve the algebra of the whole numbers, and step by step, we were killing homotopy group cycles whatsoever. But this is tree shaping. Okay, so and here we resolved the operad as step by step. Trust me, it works. If you don't trust me, go back to Stachef stages. So now this gives you a quasi-free resolution of that. So I claim that algebras of a data operad, they have nice homotopy properties. And this is exactly A infinity algebras as defined by Stachef. And we know that they have the nice homotopy property. Okay. Now, the motivation for that is, look, I cannot do that all the time. John will need, in 2 weeks now, a notion of Gerstenhaber algebra up to homotopy. Will I take the operad Gerstenhaber here and step by step constructing the higher CZGs? No. So I need a method to produce all the CZGs together with a certain algebraic structure, which gives me the notion of Gerstenhaber algebra up to homotopy. And this is what Koszul duality is going to do for us. Exactly in the same way as it was doing for algebras. Okay, so this is the space of operadic CZGs. You see, so And here you see the differential is actually amounts to splitting your corollas into two. So this is a quadratic differential. So it seems to work exactly in the same way as the Koszul duality theory for algebras. Is it serious to begin Koszul duality theory now? I don't think so. I don't think so. No. Tell me. No. Okay, let's stop here. Okay, do you have questions?
Yes, I've got what are the arrangements for dinner this evening?
Oh, yeah, thank you. So we plan to leave the institute at 6, to walk in the city, sit in a nice place, have a drink, and eat at the same place. So can you raise your hand if you want to join, so that we see and we call them, and alors, on y va. 2, 4, 6, 8, 10, 11, 12. Okay, so we meet here at 6, and if you want to join us there, I think we're going to Bill's restaurant. That's the name of the place we were.